Okay, hello everyone, and thank you for joining. Welcome to the Breakthrough Symposium, which is organized by SHAG-EC. So, a couple of words about what SHAG-EC is. So, SHAG-EC is SNS High Fair User Group Executive Committee. So, we are an organization which is run by users for users. So, we represent users who come to ORNL to do the experiments. We are point of contact, and if you have any comments, suggestions, if you have problems or some ideas, please let us know. And I put, so on the slide, you can see the SHAG webpage. So one of the reasons for us to organize that series of those breakthrough symposia is to reach out to the communities, the research communities that might be not, traditional users of neutron, but whose research program might actually benefit from using neutrons. Yeah, so the goal here is to get new users by hosting this symposium, and the focus of those symposia are on various topics where neutrons can play a vital role in solving the outstanding research problems. So on the slide, you can see the agenda for our meeting. So we have a couple of last minute changes in the scheduling for our speakers, but the major thing is that we have a stellar speakers today. And I would like to also mention that we have panelists who join at the meeting. So Naresh Oster at ORNL is one of them. We also have Hasina Belnou and Kien, who are instrument scientists at ORNL. So let me start by introducing our first speaker, Zhu Liu at ORNL, and he will talk about recent developments of operandi neutron diffraction for studying energy storage materials. So the floor is yours.
Let me share my screen. Can you see my screen?
Yes, as you can see.
Yes, we can see the screen, but could you please go into presentation mode?
Sure. Is it working?
Yes.
Yes, perfect.
Yeah, cool. Yep. Thank you. Thanks the organizer for the invitation. This is a great opportunity for me to share with you guys about some of our efforts in developing the operandi neutron diffraction for battery research. My name is Jue. I'm a diffraction instrument scientist at one of the total scattering instrument called NOMIDE at SNS. So before I start the talk, I really would like to thank our team members and collaborators who is really helping me for making this project a successful project, particularly Zhijia and Michelle, who helped design in the in situ cell and also develop the in situ sample environment for this capability, and some of my previous postdocs and students who helped a lot in the early days of developing this capability. I would also like to thank my collaborators for providing me the either the facilities to assembling the batteries or providing me high quality samples for some of the studies. And I would like also to thank our wonderful diffraction team. As you can see here, we are a really big family here, particularly the team members at the instrument I'm working on, it's NOMIDE. Lastly, I think I would like to thank the funding support, which is the Lab Director Research funding for developing this capability. So I think since I swapped, the last minute swapped between me and Shirley, so I decided to put the one slide here, a very brief introduction about lithium-ion battery. As many of you know, we used lithium-ion battery daily for the portable electronics, like cell phones or laptops. This is really a fascinating device. It's very effectively converting between the electric energy and the chemical energy which also allows very high efficiency in converting between these two resources. So this has been awarded the Nobel Prize in 2019 in the chemistry. So I think you can also see there is really a lot of efforts in pushing for a more electrified society, right? So moving from not only the portable electronic devices, but also more into the transportation sectors. So in that sense, a good understanding and improvements of the current lithium-ion battery technology is critical, you know, when you think about large scales applications of this kind of energy storage device, not only for transportation, but a lot of cases also for, you know, great energy storage, for example. So when we're looking at the battery, especially the lithium-ion batteries, which is really a complex multiple scale problems, you know, in both of the length scales and also in time scales. For example, in a device-wise, right, when we look at the, for example, the battery package in the electric vehicles, which are in the meter scales, and then we can go to a single battery like a cylindrical cell or pouch cell, and reaches in the tens of centimeter scales, all the way down to, for example, the materials that make these batteries, for example, the electrode materials, which has this secondary particle or primary particle, which are in the you know, tens of micrometer down to nanometer scales. And when we try to do the so-called bottom-up approach in a battery innovation, we typically start looking at the, you know, atomic scale level, which has the dimensions of angstroms, right? So, but from the other, you know, scale, which is the time scale point of view, you see that when we're looking at the cycling life of the batteries, which are operating in years or even tens of years, right? And you think about one charge and discharge of the battery, which typically happens in minutes to hours. And when we look at the basic research of the battery materials, what are we looking at? For example, the ion dynamics, right? The macroscopic diffusion, which happens between the, for example, the 10 picoseconds all the way to milliseconds level. So it's really a very complex multiple scale problem if we really try to achieve the so-called bottom-up approach for this innovation, which requires us to understand the devices at the battery system at the levels of the electrons, ions, and all the way to the particle and finally to the device level. So which requires a comprehensive, you know, multiple model characterization of this type of system. And that's why neutron scattering can be very useful, because as many of you already know that when we're doing neutron scattering experiment, we are probing both the energy space and also the momentum transfer space, right? Because the neutrons that we used to probe the dynamics, for example, really has falls into a region that is really relevant not only to the dynamics of the material, but particularly relevant to the dynamics that we are interested in a lot of battery system. For example, the ion dynamics, the diffusions of ions, and to a lot of interesting phase transitions in the battery materials, and also, you know, to the molecular vibrations in, for example, the liquid or polymer electrolyte, right? So when we're talking about the static structure-wise, the neutron diffraction, which assumes we don't have any energy loss during the scattering process, can also probe in length scale-wise, a different length scale. For example, if we're interested in the atomic structures, we typically go to a large momentum transfer. And if you're interested in a lot of large scale structures, for example, porosity in the battery electrode, then we go to a very small momentum transfer using a small angle neutron scattering, right? So from this picture, and then if we just project this picture into a more of a, you know, related to the battery system, it's really highlight neutron scattering can provide a lot of unique opportunity to characterize phenomena that is it's important for understanding the battery system. For example, so a lot of times we use quasi-elastic neutron scattering to probe the lithium or sodium ion diffusions, right? And to go a little bit further, for example, you can study how the lattice dynamic can affect specific phase transitions in the battery materials, and also the atomic structures, large scale structures. There are also other unique neutron scattering related technique. For example, the neutron reflectometers, which can allow us to probe the interfacial structures in a thin film battery, for example. And also when we're interested in, for example, the lithium dendrite growth or cell degradation mechanism, neutron imaging can be very useful. So because neutron scattering is a very broad technique, and due to both the time limitation and also the limitation of my own expertise, I will just confine myself to talk about the diffraction technique for today's talk, particularly on the operando side. So neutron diffraction is very useful for the study of the battery materials. There are few unique advantages. One of them, I think, has been highlighted for many times, is that it can be used to detect light elements, even in the presence of very heavy elements, right? Because of the reasonably large coherent scattering length of these light elements. One good example is very relevant to the study of lithium-ion battery is the lithium and oxygen, and to a large extent also carbon, which has been broadly used as an anode for the lithium-ion battery. So it can also distinguish, the neighboring 3D transition models. This row here, which are very important for the lithium-ion battery cathode, right? As you probably notice when you're doing the battery research, a lot of the battery cathodes actually contains multiple of the cations in this row. So because of the sitting next to each other, they have very similar X-ray scattering power. So it's sometimes we don't have a good contrast from both, X-ray diffraction and electron diffraction point of view. But neutron diffraction can provide a very good contrast for a lot of them. So, and I also want to highlight a bit, that does not mean that, neutron diffraction is better than X-ray diffraction. A lot of times, neutron scattering and X-ray scattering really provide a very complementary tool to each other if you do a combined type of study that can provide a further layer of contrast. So this part is the bit I really want to highlight, because that's it's directly relevant to what I'm going to talk about today. That is, neutrons are strongly penetrating and it's non-destructive. Okay, so that's a unique advantage neutron scattering has compared to X-ray scattering. If you are familiar with using in situ X-ray diffraction to study the batteries during the operational conditions, you probably notice a lot of times we use a very high energy X-ray, and they can cause some, side reactions or phase, transition delays when you try to monitor structure transition. But that will not happen when you try to use neutron diffraction to do that. So that's a really good or unique advantage of using neutron diffraction for the operando type of studies. So the next question is, since we already can use neutron diffraction to do a lot of ex situ studies on the battery materials, why do we need operando, right? So why don't we just, charge a battery to a specific state and then extract the material and then do the characterization, right? Here is a good example. I hope that this convinces you that it's important to monitor the structure transition during the operational condition. It's a sodium-ion cathode. It's a layered cathode with two different elements on the transition metal layer, one nickel and one manganese. When we try to charge the material to high voltage, take sodium out, and then we can, stop the battery and extract the electrode material, and then try to characterize that. And we will notice, okay, there's some interesting structure changes, right? Because you see a new peak formed, and this is a peak that is related to the layer dimensions along the interlayered material of the C-axis. And there must be some new phase formed when we try to do structure studies using the X-ray samples, right? Even you carefully seal the sample and, using very high resolution diffraction data. And then if we do an in situ diffraction study on an in situ cell, you will immediately notice there is only two phase transitions at different stages, right? Take 1/3 of sodium out, take another 1/3 of the sodium out from the system, but there's no peak here, right? So this highlight, a lot of intermediate phases formed during the electrochemical delithiation or dissociation process, actually are monostable. That means like when we relax the battery, the structure also relaxed. So we are not probing, the structure evolution or structure changes that happened during the operational conditions. And even with X-ray diffraction, we can see the structure changes, but it cannot provide good contrast a lot of times, for example, between the nickel and the manganese, right? So that's really when the neutron scattering comes in, provide a good contrast for the neighboring transition metal cations. It can also be very sensitive to oxygen, for example. A lot of times, if you're interested in the material structure, the cathode material charged to high voltage, you will notice that probe of oxygen environment change is critical. So the other thing, last thing, of course, is less destructive and going to not disturb the electrochemical reaction. So operando neutron diffraction, the idea actually comes, probably at the same time when the X-ray in situ or operando X-ray diffraction was developed. And I think for the last few decades, there are a lot of effort in pushing this towards the level of in situ X-ray diffraction. And you can see here, I just took some of the reported cell configurations that has been used in the literature. This has been tested both on the constant wavelength diffractometers and also on the ablation, source-based diffractometer or time-of-flight instrument. So we tried part cell, coin cells, also cylindrical cells using the thick pellet. This work has actually been done on Powergen and also some of the early jelly roll cells. If you look at these different configurations, there is one thing that it really differs this from a typical in situ X-ray diffraction. That is, we need to have large amounts of samples in the beam, and because of the relatively lower neutron flux. And a lot of times we have to sacrifice between electrochemistry and a good neutron diffraction data. So that leads to a lot of not so reproducible experimental results. So this really calls us to design, a new type of in situ cell that can, provide not only reproducible electrochemistry, but also have a very can also provide a very high quality diffraction data simultaneously in a faster data acquisition configuration. So this also needs to be high throughput. So the reason we need high throughput, as many of you know, that neutron diffraction or neutron sources in general is a very scarce source. So if we just do this one-shot experiment, right? So this is not a very effective way of using the neutron beam time. So we really need to achieve this high throughput measurements of multiple cells, sequentially or simultaneously. So this inspired us to put efforts in this project is on the high throughput operando neutron diffraction capability to study the lithium or sodium ion batteries. So we designed this new type of in situ cell, as you can see here, which is made a thin wall cell body, as you can see here. And when we roll the pot into the jelly roll configuration and put into this thin wall quartz tube, and we have this sample environment bracket, as you can see here, which allow us to put multiple of these newly designed cells on the bracket. So in this configuration, what we can do is we can collect neutron diffraction data on one of the sample, for example, one for a few minutes, and then move to the next one and to the next one. So this allows a high throughput sequential measurement of multiple of the cells. And if you're interested in only doing, for example, very fast charge or discharge, then you can also stick to one of the cells. So the good thing about this design is that this allows the users to easily fabricate very large amounts of a customized in situ cell. So, instead of, the very costly Tizer cells, you can see some of the old examples. And they also minimize the background that we typically get from an old version of the cells. So then we can have a experimental setup, as you can see here. This is the cell, and this is a detector, configuration nomad. And this is after detector coverage upgrade. So we have a full population of detectors in this, in this Debashore comb. So it's very large detector coverage. And this is our beamline associated Michel, me happily loading this bracket of 4 in situ cells. So we are very happy. So the data must be very good. It's indeed very good data, can be collected. So we can monitor both the batteries, electrochemistry, and data collection. And we can do on-the-fly data reduction and data analysis. So this is a capability we developed in the last few years, and is also fully available to the general user now. So very importantly, let's do some data quality assessment, right? We can achieve reasonable reproducible electrochemistry, but we have to make sure that the collected neutron diffraction data allows a quantitative or qualitative structure analysis. So we can operate the cell in both slow rate and fast rate. So this is a full cell, which means the cathode it has a cathode and also a non-lithium metal anode, which is a graphite. So graphite is a really perfect test case to test the quality of this in situ neutron cell, because it has this multiple phase transitions, as you can see here. If you insert lithium into the graphite, it goes to so-called staging phases. So it's not going to homogeneously insert lithium in this all the layers, but it's going to follow a staging sequential. So it first go to the so-called stage 3 phase, and then go to stage 2 phase. That means like every outer layer, you will have a lithium inserted, and finally you're going to have the stage 1 phase, as you can see here. So this perfectly captures all the phase transitions for the graphite. We can also, monitoring the structure transitions for the cathode side. If we go to the fast rate mode, that means you want to collect the charge the discharge the battery very quickly. For example, in 10 minutes, you can this cell and also data collection also allows you to do that. As you can see here, then you can do a slow rate and then discharge and go to a higher and higher rate. So this allows a structure studies on the very faster rate charge or discharge rate. So this is kind of also relevant. So then I will give you a very simple example because we have developed this capability. So now let's check how good or how useful this will be for study some of the scientific questions. So the example I want to give you here is a very interesting phenomenon. It's called the universal pool capacity retention in the nickel-rich cathodes. When you charge more than 75% lithium out from the system, universally you will get a very poor capacity retention in this material. This material itself is very important. It's probably one of the most important candidates to power the electrical vehicles. A few years back, Professor John Dunn's group published this very interesting paper. They surveyed about tens of different commercial available nickel-rich cathode material. They found a universal kind of rule. When you charge the material to over about 210 milliamp hour per gram capacity, that's about 75% of lithium, and you will have this universal decrease of the capacity retention. There are a lot of hypotheses about what happened in this material. So, to understand this, a lot of hypotheses has been proposed, ranges from microcracking to surface sporadic reaction and oxygen evolution. But when we survey different compositions, if they have the same phenomena, it seems like this is caused universally by structure changes rather than some of the parasitic reactions happens on the surface. So this inspired us to do this sequential studies, using this sequential capability to study different compositioned nickel-rich cathode to see whether there is some universal structure changes that can correlate with this behavior. So as you can see here, we put 4 different compositions here in a full cell configuration, and then this is the in situ diffraction data, as you can see here. It's very high quality data, so we can monitor in both the graphite structure changes and also cathode structure changes. So qualitatively, this allows us to monitor the structure changes. And the most important question is, can we do a quantitative structure refinement? Yes, so this is really a unique advantage of carry out this type of study at the time of flight instrument, because this allows you to get high quality diffraction data all the way to very small d-spacings. As you can see here, this is important when you do structure refinements for example, detailed occupancy refinements and detailed atomic displacement refinements. So this is showcase some parametric refinement results, as you can see here. And then we can not only get the lattice parameter information when we try to do the structure refinements. As you can see here, you immediately notice there's kind of universal kind of lattice parameter changes. That is the collapsing of the volume at about I think it's about 70% dilithiation, as you can see here, for different compositions. What more interestingly is that when we look at the detailed bond length changes, this is a really bit of interesting information. You will notice like there is a universal decrease of the bond length, which makes sense, right? When you take lithium out, you need to oxidize something in the system, and the transition metal oxygen bonds decreases. But there is a enormous increase of the bond length happened when you reach about 75% dilithiation. So that's something very unique. And based on the conventional understanding of the type of system, which is the competition between the decrease of the lithium screening effect between 2 lithium layers and the increase of transition metal covalency when you take lithium out or oxidize the transition metal or oxygen in the system. So this bit of enormous increase of the metal oxygen bonds is really something we don't understand at this moment, but that is coincidentally correlated with the phenomena that has been observed in this surveillance type of study. So there must be something happened here, right? That we don't understand at the moment. So then we decided to go back to look at the substitute undoped compound, which is a parent compound. It's called lithium nickel oxide. And strictly speaking, it's very difficult directly since the full stoichiometry of this compound. There is a few percent of nickel substitute into the lithium side. This material will not follow the perfect solid solution reactions you see for the typical nickel-rich cathode. It will have multiple phase transitions, but regardless of the phase transition, when you look at the bond length changes, as you can see here, it will have this kind of enormous increase of the bond, similarly to what we observed for the cation substitute nickel-rich cathode. So there's something interesting there that leads to us to the next question. So what is the reason behind this kind of enormous increase of the nickel oxygen bonds when we take more than 75% of lithium out? So this to answer this question, we probably need to take a little bit of the weak scattering signal that we have purely ignored when just analyze the Bragg diffraction data, which is the weak diffuse scattering that is underneath the Bragg diffraction data. So we have to use a technique called power distribution function, which not only uses Bragg diffraction data, but also uses the weak diffuse scattering data. So example I want to give here is a high voltage spinel. And many of you doing battery work know this is very important high voltage cathode. It's in an AB204 type spinel. And on the B side, you have 2 cations in a 1:3 ratio. When you sensitize the material under different conditions, it can form a long-range ordered structure or long-range disordered structure. We use the average structure model to feed the diffraction data, and you will see that in the residue, with the ordered phase, there is almost no residue diffuse scattering. But when for the disordered phase, you will get a lot of residue diffuse scattering. So we can either analyze the data in the reciprocal space, because the diffuse scattering signal is really strong for this type of material, or we can fully transform this oscillating signal into PDF, a power distribution function data, and then we can more clearly, from a chemistry point of view, separate the different contributions from, either nickel oxygen bond or manganese oxygen bonds. That gives you a sense. First, the nickel and the manganese are indeed ordered in a short range length scale, and we can also estimate the ordering length of this, short range ordering to about 1 nanometer. So this technique is critical for understanding the problem that I propose. Although I don't have time to fully discuss the problem, but I want to give you some hints, and that is indeed embedded in the understanding we have for this type of system. So the partner compound is lithium nickel oxide. From a chemistry point of view, I think also in the field, it has been agreed for many, many years that this is a nickel 3+ with a Young-Taylor distortion in a short length scale. This actually can be very reasonably described the average structure.
I hate to do this, but I have to give you 1 minute warning.
Sure. Yeah, I'm almost done, so I'm going to wrap up. Sorry. Yeah, so I think you can see that we will have some residues, which indicates that we will have short range structures. But if you look at the short range structures here, you clearly see that the amount of shorter length, shorter nickel oxygen bonds and longer nickel oxygen bonds is not 2-to-1 ratio for the Young-Taylor distorted state. Instead, it's more close to a 1-to-1 ratio. So that means, like, to understand the problem we observed, we probably need to go back to our understanding of the ground state of lithium nickel oxide. And we also propose that neutron power or Prandtl neutron power distribution function is needed to fully understand the charge compensation mechanism in nickel-rich cathode, because that provides information whether if it is indeed a charge disproportionality state, whether it's directly oxidized to 4+ or go to 3+ and then to 4+. So that's why this capability is critical for further understanding why we have this anomalous structure transitions in nickel-rich cathode. With that, I would like to thank you for your attention. I'm happy to answer any questions.
Thank you so much. And indeed, we have several questions, but we only are going to have time for not more than 2. So Athena Chen want to know, so very cool, how fast can NOMAD collect a decent neutron diffraction for retrieved analysis and bond length analysis?
Yeah, so for this in situ data, the data collection time speed, we can go down to about 30 seconds. Yeah, but for the PDF side, in the in situ cell, we have no successful so far. But I guess we probably need to have 5 to 10 minutes at least to get a reasonable PDF on an in situ, if we achieve in an in situ configuration. Yes.
Another question. So for operando neutron PDF experiment, is there any special requirement on the cathode additive, carbon binder, to avoid the complexity of the PDF analysis?
Yes, that's a very good question. So I think if the carbon additives, we can get rid of the hydrogen, that will be enough. So then we can quantitatively subtract the background. So the real challenge I see at the moment is really the separator, which is very difficult to deuterate at the moment. That's what I have, because it's a still ongoing project. I hope that we will have something to share with you guys, in the next 1 or 2 years. Yeah, for the operando PDF.
So there are at least 3 more questions for you, but in the interest of time, we have to move on. So could you please answer those questions in Q&A?
Sure.
Are you able to see those questions on your side?
Yes, thank you.
At Q&A, yeah. Thank you again. And let me introduce our next speaker. So we are very fortunate to have Professor Shirley Mank from University of Chicago to talk to us today. Yeah, so the screen is yours.
Thank you, Julia. And I apologize and thank Julia for stepping up and switch the sequence of talk with me. I'm very glad to be here today to talk about all solid state batteries. Can you see the screen? Okay,
Yes,
just make sure talking time is 20 or 25 minutes.
So it's 30 minutes for talk and 5 minutes for question.
Great.
And I'm going to give you 1 minute warning, if you don't mind.
Great. Yeah, thank you. Yeah, so I'm very glad to be here today. I think for all solid state batteries is one of those emerging battery technologies that have gained a lot of interest. So I will spend a little bit of time to go over some introductory content. So I think there's a lot of, I would say, attentions recently that focused on all solid state batteries. I think it's important for us to realize that it is not just replacing the electrolytes with liquid, replacing the liquid electrolytes with the solid. It is important to realize there is a main architecture design change with the possibility of solid state batteries. So for instance, in the liquid, you usually have a polypropylene or polyethylene-based electrolyte, but in the solid state, we directly use the electrolyte, making it a membrane as the separator. So there is no actual separators per se. And another important thing is to realize is that typically in the solid state batteries, and I will show you in my talk later, that there is the differences in so-called catholyte versus anolyte. And in fact, most of the anode side, there is really no electrolyte inside the anode because we typically use lithium metal, or later I will show you the 99.9% pure silicon anode. And it become a platform technology because we can actually replace cathode, the well-known NMC cathode, with all possible other type of cathode, LFP, LMFP, spinel NMO. So the excitement really comes from the possibility of solidify the architecture for the batteries. And in the typical fire triangle we're seeing for batteries, you can imagine the cathode typically is the source of the oxygen, and the batteries usually generate heat. And the key here is to be able to remove the fuel, which is the flammable electrolyte. So the abuse tolerance and the thermal stability of solid state is highly praised. And then we also introduced in our Joule perspective paper about the possibility of further increase the energy density by introducing the bipolar design. And this is one of the very exciting opportunities to build 8-volt batteries, for instance. I think the reduced in overall inactive materials leads to the increase in energy density. So all these are possibility that we can do in solid state, which is very difficult to achieve in the liquid-based electrolyte. And I also want to emphasize when we talk about the solid state, it's very important to realize that what are the major technology advancement, because as today's symposium is on the characterization, one should realize that when we move the platform from liquid to solid, the solid electrolytes play a major role. However, you can see in terms of the architecture for the high energy density solid state batteries, the first major jump in the energy density comes from the thinning of the solid electrolyte. Today, many research groups and the industry can make 30 micrometer thick thin solid electrolytes. And for the other important technology or engineering advancement is really the enabling of more than 100 micrometer thick electrodes. So extremely high loading on the cathode side. And all these architecture change posed the significant challenge for the characterization folks because first, you cannot evaporate the liquid electrolyte. You're going to we will have to find out ways how to study the so-called buried interface because all these interfaces in the device, how do we effectively probe those interfaces? So, this summarizes one of the major driving forces why we try to go and enable pure silicon and the lithium metal and eventually anode-free design. So while I think the electrochemists and the material scientists are moving to enable some of the fascinating platforms for solid-state batteries, I think the characterization folks, we should have think about how we design experiment to enable the probing of the buried interface. So I want to say that if one start from the real bulk all solid state batteries, the task is really, really daunting because in the anode side, relatively easy because we're using metallic anode with the powdered particles that are in the separator. On the cathode side, the situation is extremely complex today because that most of the solid state batteries use commercialized cathode. They still need to use carbon black binders, and typically the cathode are actually coated with certain protective layer against the solid electrolytes. And then more importantly, in all solid state batteries, because the electrolyte cannot flow, cannot go and fill the void, therefore, you could imagine that void is one of the major components that create extra interfaces. And in the industry, it is actually possible to inject liquid to improve the contact. But I think for academic research, I think injecting liquid further complicate this picture. So in my research group, we have been investing quite a lot of time to study fundamental science. So for instance, today, the example I'm going to share with everyone is actually based on a very well-known system that is originally from Oak Ridge National Lab. So I think there's no better platform to discuss this important solid-state electrolyte. And I also want to showcase the importance of building model systems for studying interfacial science and interfacial phenomena. So the advantage of LiPoN is manifold. It has fully dense, absolutely no porosity, no grain boundaries. It's amorphous on the X-ray. The typical ionic conductivity is reasonable in terms of 10 to minus 6 Siemens because the membrane is typically only a few micrometer thick. So this conductivity is acceptable. The electronic conductivity is extremely low, indicating this is a really good single ion conductor. And the voltage window, I will show you that we have reproduced everything Dr. Nasi Dardani's team has done before, and it's a stable cycling with lithium metal. However, I think there's a very, very few commercialized solid electrolyte, that as successful as LiPon. So first, let's look at the chemistry. The Li3PO4, when you kind of introduce nitrogen properly in the right place and the right composition, you can actually get a 2 magnitude order increase of ionic conductivity due to the nitrogen incorporation and the amorphization. So extremely simple system. And today I'm happy to report that there are actually reports showing atomic layer deposition is one of the versatile ways that can produce LiPon film. If we look back the history, back in 1994, there was extremely successful commercialization, pathways for the LiPon. Many companies actually looked at this as the enabler for wearable device, medical, consumer electronics, and the smart cards. It didn't happen, I think, mainly due to the difficulty in the manufacturing process, but I think the performance, particularly 2015 paper from Nancy's group, LNMO, LiPon, is quite fascinating. So my group in the last 6-7 years focused quite a lot on how we can produce LiPon with more scalable methods. So today I will show you how we can actually produce freestanding LiPon film, and hopefully that will eventually lead to more wide adoption of LiPon. But commercialization aside, I want to showcase really the beautiful chemistry or interfacial chemistry revealed by the LiPon chemistry. So this is a cell that is built with the lithium, LiPon, and LNMO. And I want to remind everyone, according to the first principle calculation results, LiPon, yes, it is stable with metallic lithium, but its stability with the cathode was not fully agreed upon. So today we're going to hopefully using neutron techniques to actually peek into the interfaces more closely. But performance-wise, we can see, this cells can cycle forever without capacity degradation. Really one of the few 5-volt batteries that against the lithium metal that showed outstanding cycling stability. So if I look at the LiPon performances versus LNMO in the same setup, but with the Gen 2 electrolyte, one of the first things we notice is that in the first cycle, there's always a small plateau around 3 volt. I think the 4-volt plateau is related to the presence of the manganese 3. So we also seem to have a little bit more manganese 3 plus in the beginning of the charging process. So this actually enabled us to look at other reports that showcase that the 3-volt potential is related to the over-lithiation in the LNMO. So we then worked collaboratively with scientists in NIST and used the neutron depth profiling, try to understand a bit better quantitatively the lithium LNMO interface. So this is the structure of the LNMO spinel. So in the spinel architecture, most of the batteries cycle between the cubic phases, but in case if it's over-lithiated, that the cubic to tetragonal phase transitions will happen. Indeed, you can insert up to 2 per formula unit for lithium in the LNMO. So in the neutron depth profiling experiment we did with NIST, the principle is quite straightforward. You have the neutron interact with the thin film that we have prepared, and from that, we prepare multiple films, one with LiPon, one without LiPon, and then the substrate only, and you can get this very high quality neutron depth profiling. And of course, there's a lot of fitting involved, and we relied on the expert in NIST, Dr. Jamie, to understand what is the nature of this LNMO LiPo interface. So I just quickly summarize is that we do see some excess lithium that is observed in the interface between LNMO and the LiPo. As a consequence, of course, the manganese valence was reduced. So this helped us later to understand the nature of the LNMO and the LiPo interface. Now, we also utilize the very local visualization tools. Many of you probably know this work from earlier cryo-EM enabling the observation of lithium LiPo interface. In fact, with cryo-EM, we observe a similar interface as Dr. Miaofang Zhi also observed in her study independently, that there is a 80 to 100 nanometer thick SEI between the lithium and the LiPo, and this interface actually is a multi-mosaic picture with lithium phosphate, lithium nitride, lithium oxide. But this interface is a very good SEI interface because it is electronically insulating and it allows ion to conduct through this layer. So the angle resolved XPS support this model. So we actually see that the nitrogen signal in the angle resolved XPS, you can clearly see it is gradient. Depth profiling is we can actually look at the different environment of the nitrogen because the bridging and apical nitrogen are necessary to be present to allow facile lithium conduction. So that also support us that we have to support our observations by conducting reactive molecular dynamic simulation and try to look at the mobility, not only just the lithium ions, but the light ions like oxygen and nitrogen. And it really indeed supported the experimental observation that oxygen and the nitrogen will interdiffuse into the lithium metal. And this is eventually the reason why we see a very complex gradient multi-mosaic interface picture between lithium and the LiPo. However, this interface is indeed self-passivating. It does not grow more than 80 to 100 nanometer. So it's good news that the lithium and the LiPo is indeed quite stable. Now, on the cathode and the LiPo interface, because our tools has, in our model system, there is no interference from carbon black or from binders. So the signals are very straightforward to interpret. So what we think happened is during the deposition, because the concentration difference between LiPo and the LNMO, there will already be a slightly over-lithiated layer of the LNMO, as I showed you previously, the neutron depth profiling data. And because of that, there's a little bit of the decomposition of the LiPo and also the reduction of the Mn3 manganese 3 at this interface, reviewed later by the electrochemical data. However, there seemed to be a kind of a self-repairing mechanism when we started cycling. This interface is indeed extremely stable, no void, no crack. And then our observation can be supported by the very detailed cryo-EM to study the LiPo-LiCo interface. As you can see, this is the before cycling, the pristine interface. There is multifacets coming from the polycrystalline LNMO film. And you can see LiPo is extremely conformal, soft, like just completely filled. There's absolutely no cracks in many hundreds of photos that we have taken. More strikingly is after 500 cycles, this interface, unlike a lot of liquid-based batteries, you're going to see a lot of spin-out rock salt transformation. Here, we definitely see very clean spin-out phases right next to the amorphous LiPo. Again, there is no crack, no voids, no delamination, and further decomposition of the LiPo. So this further confirmed by the energy loss, electron energy loss spectroscopy, but I won't dive details into the EOS data. So what I want to emphasize is to show how the LIPON in the pristine sample probably does have the decomposition product that is related to these species that are predicted previously by theory. However, you know, even with cryo-EM quantification or like complete identification of these decomposed species is quite difficult. I do want to show you this picture, you know, after the cycling, you can see between the two crystals, there's a very deep groove, about 40, 50 nanometer, and LIPON is completely filled inside. And, you know, in some areas near these sharp edges, we do observe the decomposition products that was previously predicted in the computation. So by doing that, it gives us quite a lot of confidence that we believe complete clean LIPON without any air exposure should have very interesting mechanical properties. So then my graduate student, who's now a postdoc in Lawrence Berkeley lab, started a journey to produce unique freestanding LIPON film. And this film is never exposed to CO2 or water. And I want to show you how flexible this freestanding LIPON is. And when we measure the conductivity and electronic conductivity, it is indeed exactly identical as the you know, LIPON that lies on the substrate. The data has already been published in Nature Nanotech just earlier last week. This film is about 4 micrometer thick and can be made into pretty large area. So, you know, I would say 1 stone for 2 birds. We were actually trying to study the buried interface, but because of the fundamental studies that actually inspired us to make LIPON in this kind of freestanding form, because based on the observation we have, we believe that the mechanical properties of the LIPON is very conformal and behave almost, you know, like we wouldn't call it a ceramic, but it's like a ceramic in the ultra thin form. It actually can be flexible. So with that, I think we then use this film to do some things that also quite relevant to today's effort in enabling anode-free cells. So we build this kind of architecture to enable the lithium stripping and the plating without any external stacking pressure. And this is just the very beginning of the trials. I would say the ability to make the freestanding LIPON enable us to explore the possibilities. And indeed, it is possible to deposit the lithium without any external stacking pressure in this thin film setup. And you know, with this, I think the previous company, Thin Film Battery, that who did license the Oak Ridge patent, now it's called Insurge, and they have been quite successful in enabling the large-scale fabrications of the anode-free micro batteries. And I also want to say there's another added benefit comes from you know, the enabling of the LNMO cells under 5 volt. So because we were able to cycle LNMO at a 5 volt with no binder and no carbon black, but cycle for thousands of cycles, this leads us to believe that the most of the degradation in the liquid cell is actually caused by things that are not related to LNMO. So in fact, you know, one of the added benefits is that we actually understood how robust the LNMO cathode is, and we were actually able to push the boundaries for these 5 volt cathode to the next level by replacing the carbon with new types of carbon, replace binder, and then optimize the electrolyte. So today, LNMO is completely capable of a full cell deep cycling of 1,000 cycles. And I think it should also, we are actually very thankful for the studies from the model system of LiPoN LNMO and the lithium system. So the lessons learned, I would say the jury is still out there who can first commercialize the LiPoN-based batteries. I think we still have quite a bit of challenge, but all look good from the fundamental understanding part. So I think a lot of you know that I took the job as half-time national lab, half-time academic professor. So I think that making solid-state battery into reality is a very, very daunting task, difficult. However, that the society demands us to make better batteries. So I would say that, from fundamental research all the way to OEM mass productions, I think national laboratories definitely will make major contributions. And I think that at the academic research lab, I think we did a lot of the materials discovery and screening. But for some of those architecture designs and for new emerging battery technologies, we will indeed have to think about how we can design better systems, better architectures for the new battery technology. So with that, I think I'm done, and I just go to the technology side. Yeah, so really grateful that on the LiPoN work is completely BES funded almost 10 years. And we're also very grateful for our industry supporters. And then last but not least, my solid state band, they did a great job in terms of enabling solid state batteries. I will be happy to answer questions now. Thank you.
Great, thank you so much for your presentation. So we do have time for several questions, and I also want to comment that the questions and answers are now available for the previous speaker are now available at Q&A. You can also unmute yourself and ask the question that way if you prefer. So let me begin by answering a question from the outsider of that research field. So do you envision a similar progress that will be made for the sodium-ion battery in the next years?
I think the sodium batteries will definitely gain momentum in the US. I think in the past 10 years, in fact, there are small programs in the DOE portfolios, as well as the National Science Foundation funded the project. Yeah, so indeed, my NSF career is entirely on the sodium-based electrochemistry. So we do expect, important efforts that will be put into the sodium batteries. And hopefully for, scattering community, sodium is a little bit easier than lithium.
Yeah, thanks, Sherry. That's interesting. So I have a question. So you talked a little bit about the depth profiling characterization of the lithium, forming on the interface. So do you think? I think you studied a lot of interface, right? And the neutral scattering has been broadly viewed as a bulk characterization technique. Do you think what directions would be really benefit for the community of studying the interface?
Yeah. So I hope my talk deliver this message is that so we started doing this just as a model system. We were not thinking about building a better batteries at all, because it's a basic energy science project, and then try to understand the interface and develop new tools. So during the 10-year process, we were able to basically enable cryo-EM, and we were able to explore neutron depth profiling because their system was so clean, no binder, no additive, and it's really not aimed at making better batteries. However, I think the knowledge we learned were all able to translate into the people who are making the bulk batteries. So that's, I think, the first important message. The second, I think for academia, I think this is really important because we have a booming industry that is doing a lot of the, better batteries. They can make bulk batteries way better than ours. So we really should further strengthen our unique contributions by building model system and then focus on the understanding, especially the quantitative understanding. The second thing I would say for bulk techniques is that right now the bulk techniques for solid state is still urgently needed. So I didn't have time today to talk about the pressure effect. So because we run out of time, yeah. So the pressure has a huge impact on the interfacial stability and the ion transport, and that's not understood at all. So I believe my call for everyone who work in the scattering community is not to go for those kind of making diamond gigapascal pressure, but we need to understand in the megapascal range how the ion transport and the interfacial stability is impacted. Yeah, so that's, I think, urgently needed for the future neutron and X-ray community.
Thank you. Very insightful.
Okay.
I think we do have time for one more question. So it was asked at Q&A, what is the role of alumina layer on slide 9? It's on cathode, but thicker, so not as coating layer, I believe.
Slide 9. Okay.
Slide 9, yeah.
Yeah. Yeah. So I think I think we were growing some things on the substrate, I believe. That's the substrate. Not it's a thin film. So it's not actual batteries. Yeah, it's not a coating. It's just when we study the neutron depth profilings, just to understand the interface, we use a clean substrate like the alumina substrate. So you can grow the LiPon and grow the LNMO, but it was not to cycle the batteries. It's just to study the depth profiling.
Okay, one more question just showed up. So can LiPon thin films replace Nafion membranes as solid electrolytes?
So I think the Nafion is more for the fuel cell folks. The LiPon is not stable in many of these, environments that are used in the. So I think the LiPon's only capability right now is transport the lithium ions. So the function is very different. However, I think a LiPon thin film right now is a good time for us to think about no one can make a functional LiPon films more than, say, 20-30 micron, because in the actual bulk batteries, separator are typically 20-30 micrometer thick, but LiPon's conductivity is too low. So it's only 10 to minus 6 Siemens. So if you make a 20-30 micron, it will not be operational for the bulk batteries. So I think to answer your question is the real challenge for our field is that can we make 10 to minus 3 millisiemens, 10 to minus 3 Siemens per centimeter electrolyte, like LiPon, stable with lithium, stable with LNMO, and then there's a possibility it will be as successful as Nafion film. But at the moment, such materials, it does not exist. I think LLZO is the closest. However, I think LLZO's impedance with the cathode is extremely high. So at the moment, people are still working on it. So I do think that the concept to going for Nafion style is similar, but the battery field people are still not there yet.
Okay, thank you so much. And it's time to introduce our third speaker. So Kimberly C. from Caltech.
All right. Thanks, Yulia, so much for the introduction, and thanks for inviting me to be here today to talk to you all. Just double checking that my microphone is correct. And thanks to Shirley and Jua for the great talks, and David, I look forward to yours as well. So it's a pleasure to be here. I originally gave this title focusing on anion redox, but when I sort of thought more about this symposium, I decided to make it a little broader. So I'm going to talk about today just sort of next generation battery chemistries, which is what my group is really interested in. And my goal is just to sort of give you a flavor of the types of chemistries we study so that we can understand some of the problems that we're facing and the sort of characterization roadblocks that lead to lack of understanding and places where I think neutrons could really play a big role. So the goal behind next generation chemistry, which has been alluded to in previous talks, is really to think about moving beyond the sort of conventional materials that are used in lithium-ion batteries and think about less expensive and more abundant materials so that we can target new applications. And whether that's renewable energy storage or widespread electric vehicles, we won't really know what that application is until we have a pack, but we can start to think about sort of the limitations of lithium-ion and try and go beyond those. And really, the way that my group thinks about this is that there are really three main elements that we're trying to use or trying to prevent using. One is lithium. So lithium is found, of course, in every component of the cell, in the anode, the electrolyte, and the cathode. It's our working ion. And then the other two are cobalt and nickel, which are the workhorses in the cathode. And so everything in my group is basically aimed at beyond lithium, cobalt, and nickel chemistries in one way or another. And so we have projects across the entire range of the cell. We work on metal anodes, which focus on using things like magnesium, calcium, and zinc. We work on electrolytes that conduct these unconventional ions. And we also have work on the cathode side, where we're really focused on iron-based cathodes that have similar energy densities to the materials that have nickel and cobalt, but they don't contain any nickel and cobalt. And so I'll sort of touch on on all three of these today, and maybe I'll go in a little bit more detail on the cathode side, which is where I'll start first. And so to begin this, I just want to give everyone sort of a really brief refresher on how intercalation chemistry works, because that's the cornerstone chemistry that's used in conventional cathodes. And then I'll tell you how we're trying to go beyond that to get rid of the nickel and the cobalt. And so intercalation chemistry, this TiS2 was really the first material to show electrochemical intercalation of lithium. And that was, of course, shown by Stan Whittingham, who won the Nobel Prize for that in 2019. And TiS2 is a really incredible material. It's a layered structure that can accommodate 1 mole equivalent of lithium. So you can fully delithiate and lithiate this material, and it remains in the same family of materials. There's really not a huge structure change as a function of lithiation and delithiation. And just to sort of highlight that, I'm showing the atom positions of the lithiated phase, and I'll superimpose them on top of the delithiated phase, and you can see that they're very similar. And so this lack of structural change leads to really good reversibility. So we can lithiate and delithiate this material many, many times. And the way that we think about where this electron goes for the charge compensation reaction, so anytime we introduce lithium, we have to introduce an electron. Anytime we release lithium, we have to release an electron. That electron is formally associated with the transition metal D state. So you can think about this as formal redox on the titanium, so titanium 4 reduction to titanium 3, or just filling and unfilling the D bands that are associated with titanium in the metal. And this is how conventional intercalation works, and it's really limited to 1 mole equivalent of lithium per transition metal at the most. And of course, conventional materials don't use sulfides. We use oxides, so things like lithium cobalt oxide, for instance, or this metal here can be nickel, manganese, cobalt, or aluminum. And I think Shirley just mentioned some of those types of materials, and Jue did as well. And these types of materials can do at most 1 mole equivalent of lithiation or delithiation, and usually it's much less than that. It's around 0.8 or something like that. And if you do that, you can do transition metal redox. If we think about mechanisms that go beyond this, there are these so-called lithium-rich materials that have more than 1 mole equivalent of lithium. And to form these types of materials, you have to go down the periodic table to these 4D transition metals like ruthenium. But if you do that, then you can imagine that you can deintercalate 2 mole equivalents of lithium. And then the question is, where does that electron come from? Does it come from multi-electron redox on the metal? Or can I actually invoke redox on my anions. And so there's some contribution of the oxygen P states in some cases, and the reversibility of that is sort of a question mark. So we've been very interested in this idea of anion redox and how to leverage it in order to produce more sustainable materials. But instead of using oxides, we've been very interested in sulfides. One of the reasons is that sulfides, we can use 3D transition metals and get lithium-rich chemistry. So we can make materials like Li2FeS2. This material has been known for a very long time. I have a selection of citations from the 80s down below. And this material is additionally interesting from a performance perspective because it shows very reversible electrochemistry. So in the middle here, I'm comparing a lithium-rich oxide to our lithium-rich sulfide. And what you can see is that cycle 1 and cycle 2 look very different for Li2RuO3, whereas for Li2FeS2, they lie nearly directly on top of each other. So that tells us whatever we ended up here looks very similar to what we started with, i.e. it's a more reversible redox process, even though both materials are doing multi-electron oxidation. So by that, I mean, we're doing more than 1 mole equivalent of lithium per transition metal. So in Li2FeS2, we can get this up to about 1.8 moles of electrons, which means we're down to lithium 0.2. So that's an incredible amount of delithiation in this material. And so we've been very interested in the mechanism by which Li2FeS2 is able to do reversible multi-electron redox. And so we've studied that in great detail using techniques like X-ray absorption spectroscopy. And what we found is that the redox is primarily located on the iron for the initial region of the charge curve. So if you remember, there's a sloping region here in the charge curve, and then there's a plateau region, and I'll talk about both of those regions. So that sloping region is associated with iron 2 to mixed iron 2,3, and it's really localized on the iron. There's some change in the iron sulfur covalency as a result of that iron oxidation, but it's really the workhorse is the iron D states. And then that plateau region that I showed you is associated with anion redox. So we get oxidation of sulfides to persulfides. And what's really important about that is that the formation of persulfides requires the formation of a sulfur-sulfur bond. So the rehybridization of those p orbitals to form that new bond is what stabilizes, essentially holds on the sulfur. But it also requires a structural distortion. And the way that we visualize that structural distortion is shown here. So we think what it is there's basically a corrugation of the metal layer. Once you get these sort of corner sharing iron tetrahedra, those can corrugate to form sulfur-sulfur bonds at the apex of the sulfurs in that tetrahedral coordination environment. And that's where we think that sulfur-sulfur bond is located. And this really comes from XAFS data, which tells us that things like the iron local structure is not changing, but we're sort of limited in our understanding of this structure because the long range order is changing. So things like powder X-ray diffraction, even on the synchrotron level, can't tell us a whole lot about what the structure looks like. So we've been able to modify this material and try to do things like tune the covalency and tune the electronic structure. The first thing we wanted to do was tune the covalency between the metals and the anions. And so instead of changing the iron D states, instead of changing the transition metal and pushing it further into the P states, what we did instead was shift the P states up into the metal D states. So we moved from a sulfide to a selenide. We're moving down the periodic table, so the P states are higher in energy. And so we should get a more covalent metal anion bond by doing that. And we were able to show that the Li2FeSe2 end member is isostructural to the Li2FeS2 end member. And this isn't necessarily surprising. Sulfides and selenides are often isostructural. But what this allowed us to do is actually make the entire solid solution between these two. So we made the anionic solid solution, and that allows us to systematically tune the relative position of the P states. So we sort of have a continuum of states between selenium and sulfur by doing this anionic solid solution. And what we see in the electrochemistry is maybe exactly what you would expect or maybe not. And that's that the voltage associated, or the potential that's associated with the anion oxidation, so that oxidation of sulfide to persulfide, systematically shifts down as I put selenium into the phase. So this maroon curve is my original Li2FeS2 curve. If you recall, this plateau region is oxidation of sulfide to persulfide. As I put selenium into the material, that systematically shifts down in potential because I'm essentially pushing the P states up in energy. And so what that tells me is that this material is very well mixed. So we're not doing just isolated selenium oxidation and then sulfide oxidation. Instead, we're pushing and pulling basically that frontier valence band up and down as a function of the P character near the Fermi level. And we see that directly in the electrochemistry. And if I look at the voltage as a function of the stoichiometry, I see that the voltage trends essentially linearly, which is what we would expect if we had a very well-mixed electronic material. And so this is just further evidence that the anion redox is associated with this plateau region. And by, of course, changing the energy levels of the anions, we can change the position of that voltage. The other thing we've been very interested in is the effect of vacancies. So I mentioned that there's this tetrahedral tilting mechanism that occurs in response to the formation of the persulfide. Well, that tetrahedral tilting requires a vacancy in between the tetrahedra in order for that structural distortion to occur. And so vacancies likely play a very significant role in controlling anion redox, and especially in materials that form persulfides as a result. So to probe that, we went to a different phase of materials. This is very similar to LiTIS2, so Stan Whittingham's original material, but it's lithium rich. So there's lithium in the transition metal layer to yield this different stoichiometry. So it's Li2TiS3, if you want to think about it like that, or it's a Li1.33 Ti.67S2. So we're basically just substituting lithium for titanium. And this material has a fully packed cation sublattice, and it has a D0 transition metal. So the titanium is 4+ here. And so this material has been known to do no electrochemistry. When you oxidize it, it's basically inert. And we hypothesize that's because it's not able to access the sulfur P states because we have a fully packed cationic sublattice. And so what we did was we introduced vacancies into this material by doing this substitution here, where we basically take titanium out and put titanium in and take out the lithium. And that gives us vacancies, but allows us to keep the titanium oxidation state at 4+. So we're keeping the D count at 0, but we're introducing vacancies. That allows us to see what the vacancies do to the anion redox mechanism. And what we find is that as we introduce vacancies, which is given by this Z number here, so this Z is basically the moles of vacancies per formula unit. As we introduce vacancies, the anion redox capacity basically skyrockets. So the more vacancies we put in, we get a higher capacity, and this voltage shoots straight up to the anion redox plateau. So we see no evidence of titanium oxidation, and this really is just anion redox, and it's enabled by the formation of these vacancies. And we did a lot of work to characterize the presence of vacancies, although I think neutrons can play an important role there as well, and also the charge compensation mechanism that it's localized on the sulfur. With our collaborators at UCSB, Anton van der Ven and his then student Daniel Kacevez, did some calculations on this phase. So this is now looking down the C-axis to see exactly where these persulfides are forming. I'm not going to go into detail on this slide, but what they found is that the persulfides form along the octahedral edges that are neighboring a vacancy. So the vacancy plays a big role in enabling those sulfur-sulfur bonds to pinch together along the octahedral edge and stabilize the holes on sulfur. And basically what this convex hull is showing you is that at some lithiation amounts, you can get only transition metal redox. So this is with if you have type 3 in there. But once you get to a certain regime, then you have to jump up to one of these convex hulls, which gives you the persulfide. And so what we've learned from anion redox is that sulfide oxidation results in the formation of persulfides. And we did a lot of work to show, we did some mining of the literature to show that there are many, many phases that contain persulfides that are thermodynamically stable phases, many more than contain peroxides. So persulfides are a much more accessible and much more thermodynamically stable motif. And that's really because the position of the P bands in relation to the metal D states that we have. And so the fact that they're stable allows us to do this reversibly. So we can do this sort of simple structural distortion in order to access the sulfur P states. And we think that vacancies play a huge role in contributing to anion redox. So whether it's this tetrahedral tilting in the Li2FeS2 case, or pinching along an octahedral edge that neighbors a vacancy in the titanium sulfides, vacancies seem to play a significant role because of the structural freedom that we need in order to form those bonds and to free up the p orbitals to rehybridize. And then we were able to show that we can change the covalency of the metal anion bonds, and that allows us to tune the voltage of the anion redox and not necessarily the reversibility, and that's shown again here. With all of these things, we've also been able to show that we can tune the crystal chemistry to change the charge compensation mechanism and actually increase the capacity of the material. So with this new iron-based material, we can get capacities over 450 milliamp hours per gram, and with an average voltage of about 2.5. And if you take those two together, you get an energy density of over 1,000 watt hours per kilogram, which is really exciting. So if you compare that to things like the NMCs or lithium iron phosphate, which is certainly the front runner for iron-containing materials, from an energy density perspective, they're very exciting. We still have some challenges ahead associated with hysteresis and reversibility, but I think that this is a viable way to bypass the low voltage redox associated with iron, so we can store more charge on the anions. And so there are some things, this is just sort of a list of things that I put together thinking about this symposium that I just sort of what can neutrons do for us? There are things that we still don't know and need to understand. It would be really great to measure the evolution of the local structure operando, and doing that with tools that can see lithium is very powerful. It would be great to observe the behavior of lithium in disordered systems as a function of the redox. We really don't know what the lithium is doing during the redox processes, and especially in the iron-containing materials, there's disorder on the metal site. So we don't know if those start to order or not, or what's going on there. We would like to know the exact location of cation vacancies and determine their role in structural distortions. And we would also need to know the role of magnetism in driving or even suppressing some of these phase transitions, because we're going between iron 2 and iron 3. Magnetism is no doubt playing a strong role in these things, but we don't really understand that yet. And on the metal side, so I just want to briefly tell you about what we're doing to get rid of lithium and the types of questions that we're thinking about there. So to go beyond lithium, we're thinking about things like magnesium, calcium, and zinc. Those are all divalent cations, of course. And divalent cations have the added challenge that they have a high charge density. And so one of the sort of fundamental concepts that we don't really understand is the ability of these divalent ions to diffuse in solid materials. So we don't really understand the solid state ionics of divalents. This is, of course, really important if we're going to target intercalation electrodes. It's going to be really important if we have metal anodes. And metal anodes are the only way that divalent ions are ever going to be useful in a battery chemistry, is if we can actually do metal deposition and stripping. But these metals are very reactive with electrolytes, and so they form these surface layers on the surface of the metal that I hesitate to call an SEI, because they're very ionically insulating and they shut down the electrode altogether, and it basically kills your electrochemistry. And so you're very, very sensitive to what's in your electrolyte to if your solid metal anode is going to work or not. And then, of course, if we were to think about using solid state electrolytes, which would be much less flammable, as Shirley was mentioning, than the organic electrolytes, then ion diffusion is really important. And so to study that, we've been looking at ion diffusion in electronic insulators. And the reason we've done that is really just to strip away all of the complexities of materials that we can. So if we have electronic and ionic carriers, it's really hard to decouple those two, especially with techniques like impedance spectroscopy, because sometimes those are happening on very similar timescales. And so we looked at this material. This is ZnPS3. It's a distorted honeycomb subnetwork of zinc 2+ cations. Zinc is coordinated by sulfur, and sulfur is coming from this P2S6 polyanion. And the entire material is a van der Waals gap material. It has this beautiful van der Waals gap. And it turns out that this material conducts zinc. So it's an electronic insulator that conducts zinc. And the conduction mechanism is this vacancy mediated mechanism within the metal layer. So the zinc hops to a neighboring vacancy. And the activation energy associated with zinc conduction is very, very low. So experimentally, we measure it to be around 300 MeV, which is on the order of the best lithium ion conductors. And the reason that it's low is actually because of this P2S6 polyanion. So as zinc moves through the material, there's a flex of that P2S6 polyanion. It's basically an extension of the phosphorus-phosphorus sulfur bond. And that sulfur basically impinges into the van der Waals gap where there's minimal electron density. And so the energy penalty associated with that is low. Unfortunately, the fact that it's a vacancy mediated mechanism means that we're limited by the concentration of vacancies in the material. And so in this case, we only have entropic vacancies, so the conductivity is very low. To increase the conductivity, we've looked towards other mechanisms. So what we've done is we've taken ZnPS3 and exposed it to humid air. It turns out if you take ZnPS3 and you expose it to humid air, it will absorb water, and it does it in a macroscopic way. You can see the pellet is changing shape and size, or it's changing size with different relative humidities. But what's really interesting is that the conductivity, which is shown here, increases by over 5 orders of magnitude as a result of incorporating water into the structure. And so we found that that conductivity increase is associated with both zinc conduction and proton conduction. So we have two carriers in the system. And by electrochemical methods, we can sort of decouple those two with sort of a large error bar. And we found that about half of the current is carried by zinc. So even with a large error bar, that's a very high conductivity of zinc. And so we're pretty excited about that. The mechanism by which this is happening, we think, is that we have this material, which is a pellet. When we expose it to water, water is actually absorbed at the grain boundaries. We don't see any evidence in the crystallography that water is going to the crystal structure. So we see the 001 stays in its place as we put water in. So it's not going in the van der Waals gap. There's really no driving force for it until we get to these higher water concentrations where we start seeing new reflections, and we're studying those phase transitions now. But as water goes into the grain boundaries, zinc can basically desolvate from the ZnPS3 and solvate into the water layer, and we can get conduction in the water layer. And so this is just an interesting mechanism for zinc ion conduction. It's basically leaving its anion behind in the solid. But this leaves us with many challenges associated with characterization, because now we're using these sort of weird cations like zinc that aren't very good NMR nuclei. And it makes it hard to measure diffusion without an electrochemical cell. So the things we'd really like to be able to do would be to measure the dynamics of ions that are not NMR active, independent of cell considerations. So we don't have to worry about pelletizing or interfaces. If you've ever done a measurement on a solid state electrochemical device, it's very finicky. So if we can get away from that, that would be great. We really want to be able to decouple the dynamics of multiple ions. We want to be able to probe the correlation between phonons and ions. I mentioned that the distortion of the material facilitates ion diffusion. It would be really great to see the ions move at relevant timescales so we can actually observe migration paths. And we would also like to be able to rigorously characterize defects and correlate them to the dynamics. And so I have to thank everybody that worked on these projects. I have a great group of students and postdocs and undergraduates who I've worked with. Another great group of collaborators, and of course our funding sources. And thanks again to the organizers for the invitation to talk to you all.
Great, thank you so much for the very stimulating talk. So there are a couple of questions. So the first one, and I think it's for the first part of your talk. So what is the physical meaning behind the slope charge discharge curve for iron, and why does the chalcogenides redox plateau?
Yeah, so I didn't have a whole lot of time to get into detail about the electrochemistry, so thanks for that question. So normally when you think about the shape of a galvanostatic charge or discharge profile, if you see a sloping region, then we associate that with a potential that's changing as a function of stoichiometry. And so you can think about that as like a solid solution type behavior. So for an intercalation mechanism, you know, like lithium cobalt oxide, when it lithiates as a solid solution. So you get, you know, you basically just sort of fill up the Fermi level or take it down. And so you're basically measuring that directly with the electrochemistry. When you see a plateau, that means that your potential is pinned as a function of stoichiometry. So your potential is not changing. And that's usually indicative of a two-phase reaction. So that means that you have, let's say, you know, 1 degree of lithiation and another degree of lithiation, and you're just interconverting between those two, and the presence of those two pins your potential. So that's where those come from. Although we have to remember that those profiles are measured off equilibrium, and those are very equilibrium pictures that I just described. So there's also kinetics associated with that. So you can have kinetics that can smear out those profiles in different ways.
Okay. Thank you. And I think, so Shirley, do you want to unmute yourself and ask your question?
Sure, yeah. Thank you, Kim. Very interesting findings. I typed the 2 questions, but I don't know how to paste in the Q&A. I'm still not so skilled with Zoom. I can't believe it. So first question is for your anion redox active sulfide materials. Did you measure electronic conductivities? Do you know the magnitude order for their, because for electrode materials, you know, the mixed conductor would be preferred. So that's the first question. The second question regarding the zinc conductive materials, which is extremely interesting. The approach you use is introducing proton, but I wonder if you have tried to introducing more defects, you know, because you seem to know the mechanism quite well. I was just wondering if amorphizations was introduced for further improve the conductivity.
Yeah, thanks, Shirley, for those questions. So for the iron sulfide, Li2FeS2 is a black material. It's a pretty, I don't remember the conductivity off the top of my head, but it's a pretty good conductor. What I don't know is its conductivity as a function of delithiation. So we haven't measured that, and we should figure that out because it will certainly be changing, especially because we see a phase transition. So, but it's a
black is a good, yeah, at least the indicator.
So that's good. And then for the zinc, we did try to introduce vacancies by doing allovalent substitution of the zinc. So we tried putting in trivalent metals like aluminum or gallium or germanium. So every time we did that, we could make the solid solution no problem. That phase made solid solutions like gangbusters. It's like the best material ever to do substitutions, but it always changed color. And so we got really nervous every time that happened, that we didn't understand the electronics. And so we wouldn't know what we were really measuring with the impedance. So we sort of shied away from that because we don't have a good way of decoupling the ionics and the electronics.
Thank you.
So I think we can get one more question answered. So is the lithium intercalation reversible when titanium vacancies are created?
Yeah, that's an interesting question. That material has a very weird hysteresis that happens. So we can put, okay, so when we put vacancies in the phase and we activate the anion oxidation, what we're doing is we're delithiating at that point. So we're charging the material. We can lithiate after we've charged it. So we can oxidize and delithiate, and then we can reduce and lithiate. But what happens is you actually start to invoke titanium reduction. So we started with titanium 4. When we lithiate, there's an interesting interplay between the kinetics of anion redox and transition metal redox. So when we lithiate, we actually start to see titanium reduction instead of all persulfide reduction. And so we invoke titanium reduction. So we can actually lithiate to the degree that we started with, but we can over lithiate because then we have more titanium D states and we have vacancies in the phase. And so we can occupy those vacancies that we started with and get over reduction. But now, because we have titanium 3 in the material, the second charge doesn't look like the first charge because your mechanism is different. So yes, it's reversible, but maybe not. If you're asking if it's like thermodynamically reversible and that we see these really nice reversible curves, the answer is no, because we start to invoke titanium reduction.
Okay, thank you again. And now it's time to introduce our final speaker. So David Quabi from University of Michigan.
Okay, can you hear me?
Yes, we can hear you and we can see your screen. Perfect.
Can you see my screen? Okay. Okay, great. So thank you very much for the introduction to share some of my work with you all today. And my intention today is just to give you a little snapshot of some of my group's activities on probing chemical and electrochemical processes and organic flow batteries. Now, because I'm the only speaker, I guess, talking about flow batteries today, I thought I'll say a few words about why they're interesting, why we like to study them. And there's a schematic here of a flow battery to help me do that. So the what's unique about flow batteries is that they store charge not in solid materials, as we've seen already in the last 3 talks, but in redox active molecules that are dissolved in liquid form. So the way that these batteries work is that you typically have 2 tanks that have your redox active molecules or species, one called a negative electrolyte, the other the positive electrolyte. And you essentially store or release electricity by pumping these electrolytes into an electrochemical cell where you have redox reactions that help you deliver or store electricity. Okay. So in state-of-the-art flow batteries, you tend to have vanadium-based species storing your charge. So you have essentially what's called a vanadium redox flow battery. And what's unique about this architecture, the reason people are very interested in it, is that your energy and power are decoupled. So If you want to store more energy, you simply increase the size of your tank or increase the concentration of materials that are stored in the tank. But if you want to increase your power capacity, you increase the size of your stack independently. Okay. So with this architecture, it turns out that as you increase the ratio of energy to power, which is also called your discharge duration, the cost of your system just asymptotes to the chemical cost of the material that's stored in that's actually storing your charge. Okay. So at really high discharge durations, which are being targeted for long duration energy storage, the cost of your system can go below that of lithium-ion batteries. Okay, and it really depends on what's actually stored in the charge here. So for vanadium, you can see that your cost is sort of competitive with lithium-ion batteries at long duration, but in principle, if you can find new material with the right combination of cost and high cell voltage, you can get to system costs that are considerably lower than lithium-ion for long duration applications. Okay, and so for that reason, people have been very interested in looking at organic molecules as a lower cost alternative to vanadium in these systems. But what this plot doesn't necessarily show is the fact that capacity retention is actually a pretty important metric to consider as well, in addition to costs, in order for these systems to become viable. Okay, and this is illustrated in a nice point by the Bouchette group recently, where they calculated the levelized cost of stored electricity as a function of the rate at which you lose your electrolyte. And it is for two systems. So you have a vanadium flow battery that has a high cost, but an infinite electrolyte lifetime, and a hypothetical sort of low cost flow battery system that has lower cost, but that you need to replace every once in a while because you have some sort of finite decay rate. And what they showed is that if you have a large enough decay rate, then the levelized cost of stored electricity can actually be higher for the nominally low cost system because you had to pay for frequent replacement of the electrolyte. Okay, so really understanding or improving upon capacity retention is a really important metric to consider in these systems. If you look at organic flow battery chemistry that have been studied in the literature, you'll see that the fade rates that have been measured are quite a bit higher than 0.1% per day. That was sort of identified in this previous study as a threshold below which organics will probably be competitive. Okay. So there's a pressing need to really understand and improve upon capacity retention in these systems, and that has to do with this question has to do with what a lot of my group does in this area. Okay. So one mechanism for capacity loss in these systems is, of course, crossover, where you have one molecule from one electrolyte tank essentially diffusing across your electrochemical cell to the other. But it turns out that for most of the chemistries that I showed before in the previous slide, degradation or decomposition of the molecules is what really drives capacity fade. Okay, so organics, it turns out organic molecules decompose according to a wide variety of mechanisms and pathways. And what we ideally want to know for further development of these systems is, for a given molecule, which model or which mechanism is the correct one. We'd also like to know what the decay rates are, so what the numbers, what sort of the actual rates are for all the transitions I'm showing in these examples here. And also whether these rates are modified under operando conditions, which is to say when the molecule is actually being cycled in a flow battery. Okay. So we decided to take a look at these questions using as a model system a disulfonated orthobenzoquinone, which I'm going to call BQDS, which is appealing because it has a really high redox potential, so it's appropriate as a positive electrolyte material in aqueous flow batteries, and it also has a really high solubility at around 4 molar. It turns out we're not the first people to look at this molecule. There's been work dating back to a little over a decade, showing that when you oxidize BQDS, or when you have BQDS in its oxidized form, it undergoes either one or two Michael addition reactions, which is to say reactions with water, to form reduced species that have a lower redox potential than the original, the starting redox couple. And of course, this is something you don't want for a positive electrolyte material. Right? So in looking at this, in looking at this work, of course, one of the important questions is which of these models is correct, whether you have, do we have one or do we have two Michael addition reactions? We also want to know what the rates are for each of these pathways, or in whichever pathway is actually the correct one. And of course, we want to know whether these rates are perturbed under operando conditions. So these are questions that we set out to answer with spectroscopy. And our approach was dependent on the fact that Michael attack was expected to result in the formation of reduced species. And so we decided to track that reaction spectroscopically using potassium dichromate. Okay, so the idea is that dichromate is a strong oxidant, and in principle, it should oxidize any reduced species that are formed as a result of Michael attack. So if you put dichromate and BQDS together, just in a vial, and measure the concentration of dichromate over time, that reduction in concentration should correspond to the rate of Michael attack. Okay, so we measured the amount of dichromate consumed in this sort of reaction for various initial concentrations of dichromate and BQDS, as you can see here. And if you normalize all of the data, the concentration data, to the same BQDS concentration, we find that all of the data essentially collapses onto the same line. So what this tells us is that we have first order kinetics that's essentially governing the consumption of dichromate. But you'll see that there's actually some scatter in the data, despite the fact that they more or less fall along the same trend. Okay. So what we then sought to do was to determine what sort of kinetic model would account for the observations that we're seeing. So you can imagine in principle that you have one Michael attack reaction. So you can call that sort of model one, where you just have one addition of water. You can have two additions of water, you can call that model two. You can have three additions, and you can elaborate models. You can have as many as you like. In this particular study, we only looked at three possibilities. And what we wanted to know was, among these possibilities, which was the most likely given the data that I've just shown in the previous slide. Okay, so a very natural framework for answering this sort of question is probability theory, in which using Bayes' rule, for example, one can take the prior probability of one of these models being true, and then using the data that you obtain, you can compute a posterior probability, which is to say the probability of all of these models being true given the data that you do observe, which is the term here in red. Okay. So we went through this Bayesian inference protocol, which is what it's called, and we're actually able to compute probabilities for the three possibilities. You can actually read more about it in this paper that I just released a few months ago. But the upshot here is that the model with two transitions was the most likely of the three that we considered. What we then did was adapted or look. Sorry, we actually sort of converted this Bayesian inference protocol into estimating the rate constants for the two transitions that we believed were involved in the Michael attack reactions that this molecule undergoes, and found a probability density for those two rates, and those are what are shown here in the red dot. Okay. So all this data, actually, all these rate constants that I've just shown are applicable for a situation where there's no cycling. The molecule is just sort of being, we're just looking at the XCT decomposition of the molecule. The next thing we did was to try to figure out if those rates translated to a situation where the molecule was actually being cycled in a flow cell under operando conditions. So to answer this question, we again turned to spectroscopy, but this time we reconfigured our flow cell in such a way that we could take spectra of the electrolyte over time. Okay, so here's a time-lapse video of oxidation of BQDS Actually, I don't know if it'll play. It looks like it's not allowing me to. Yeah, so here's a time-lapse video of that oxidation process. And what I'll point out here is that we don't have any dichromate in solution. So what you're seeing is the spectrum of BQDS and all the products of oxidation and micro attack all represented on your screen here. So to try to extract kinetic data from all of this information, it's worth recalling Beer's law, or Beer-Lambert's law, which holds that at a given wavelength, the absorbance that you measure is just a product of the concentration of the species present and molar absorptivity. And you essentially just sum up these products for all the species that are present. So if you consider the fact that we're taking absorbance as a function of time, we can represent all our data with what I'll call an absorbance matrix, in which every row is just a time point, and every column would be absorbance at a specific wavelength. Okay, so it turns out that you can express this matrix in terms of two submatrices, so a concentration matrix, where n here is the number of unique components in your system, and a molar absorptivity matrix, which contains the pure spectra of each species present. Okay, so this is really just a matrix representation of Beer-Lambert's law. And the takeaway here is that by decomposing the absorbance matrix, which is what we get from our experiment, into these two submatrices, we can get kinetic data because we're able to access concentration as a function of time for all of these species. So we turn to an algorithm called multivariate curve resolution that actually helped us to decompose this absorbance matrix as I've just described, and we're able to then extract the kinetic data from this experiment. So here are the results of the analysis. You can see here that we're able to look at concentration profiles for all the 4 species involved during the oxidation, the electrochemical oxidation process. We're able to get pure spectra of all the species present as well. And by fitting the concentration profiles to kinetic equations where we have rate constants describing electrochemical oxidation and micro attack, we can actually now compare the rate constants we get under operando conditions to what we got ex situ. And what you see is that the agreement is quite close. So the green dot and the red dot are actually quite close together. So this is actually reassuring because we're seeing good agreement between the operando and the ex situ chemical experiment. And we also noticed that there's an order of magnitude difference between the micro attack for the first addition of water and the second addition of water. Okay, so there's one of them is 10 to the minus 4 seconds per second, the other is 10 to the minus 5. Okay. So we try to make some mechanistic sense of these rate constants with some DFT analysis. And long story short, what we found is that the overall free energy for adding water in the first step is actually much more negative than the second step. So that sort of agrees with our experimental data. And again, adding water, the very first sort of elementary step where we add water to the molecule is much more exothermic, if you like, or has a lower energy barrier in the first step versus the second step. So both of these observations are qualitatively consistent with what we've observed by experiment. Thinking a bit more broadly, I should also mention that there's been some computational work in the literature suggesting that there's some sort of trade-off between a quinone's susceptibility to micro attack and redox potential. You can see here that as we increase our redox potential, the free energy for micro attack is more and more negative. So this is a trade-off that has been hypothesized in the literature, but careful measurements of the kinetics that I've shown just now in principle can help substantiate this relationship. And perhaps we can actually find molecules that break this apparent scaling relationship between redox potential and the micro attack reaction. Okay, so another benefit of these sorts of measurements is that we can actually start to, in principle, simulate capacity retention by taking the rate constants that we measure at the sort of molecular level and feeding them into models that can help us predict capacity retention at the cell level. So we've actually done a little bit of this work ourselves and formulating a zero-dimensional model that can take into account your cycling protocol and all the electrochemical parameters of your electrochemical cell. And then in sort of collaboration, I guess, with what you know of the decay mechanism of the molecule, you can then sort of predict capacity fade under different conditions. So this plot just shows that in the absence of capacity fade, our experiments and simulation agree very well. And we've shown in this paper that you can read more about here that you can, for various cycling protocols and sort of electrochemical operating parameters, you can predict capacity fade or simulate capacity fade under different conditions. So in principle, this sort of brings up the paradigm or brings us to the paradigm of sort of flow battery lifetime predictions and the different duty cycles and so on. Okay, so in the little time I have left, I just wanted to mention that we're trying to extend the techniques that I just described to new chemistries. So we've recently become very excited about quinoxalins, which are interesting molecules because they have really low redox potentials and have really high solubilities. But the problem with them is that they decompose quite quickly. So we've done a lot of flow cell cycling on this particular molecule. We determined that it undergoes a two-step decomposition. The reduced form of this molecule undergoes a two-step decomposition from into a tautomer, right? One form of which is redox recoverable, and another form which is not recoverable. And we did this again using the spectroscopic techniques I've introduced. And what we then did, having figured out that tautomerization was sort of was essentially our main mode of decomposition, was to use DFT to screen a variety of molecules that we suspected would have different tautomerization energetics. And we picked the most energetic molecule in the series here and cycled it. You can see that compared to the starting molecule the first molecule that we analyzed in depth, we have a much more stable system, or a much more stable molecule during flow cell cycling. We actually figured out that most of the capacity fade we're seeing here was from crossover of the molecule from one electrolyte tank to the other. And so we put together a mixed symmetric cell, which showed really excellent capacity retention. So this is now in the absence of any diffusion-driven crossover. We're not seeing much capacity fade here. We have to actually probably cycle this for several weeks before we can actually get a number, a fade rate that we can fit a line to. And to our knowledge, this is sort of the first or the best performing quinoxalin that we've studied or we've seen in alkaline flow bed. Okay, so with that, I thought I'll just summarize the work I've shown to you. That we've done a lot on combining matrix decomposition and Bayesian inference techniques to elucidate charge carrier decay from spectroscopic data. This information can be combined with zero-dimensional modeling to predict and explain capacity retention. And in principle, we can use some of the quantitative insights we've learned to inform the synthesis of new molecules. So with that, I'd like to acknowledge the people who've been involved in this work. We've had collaborators here at the University of Michigan who've been helping us with the Bayesian inference and the DFT analysis, and we have funding from the NSF for this work. So with that, thank you for your attention. I'm happy to take any questions.
Thank you, David. So we now do have time for a couple of questions. So you can either pose them at Q&A or unmute yourself and ask a question.
Julia, can I ask a question?
Absolutely. Go ahead.
Okay. David, thanks for sharing the latest, I guess, the molecules with extremely low capacity phase. Can you put the slides on again? Maybe
Yes.
just help us to understand a bit what is the key enabling factor for the, like, this, what's the unique characters of this two, I guess, I don't know how to pronounce it, but
Yeah.
seems like I don't know, it's more like got rid of the side chain and so could you emphasize a bit of the design rules, how you minimize?
Yeah. So a lot of that is actually in this paper, which we're like about to submit this week. But what we found is that, so if I go back one slide, I couldn't get to talk about all the mechanistic details here, but essentially what tautomerization is a migration of a proton or hydrogen atom along the backbone of the aromatic molecule. So if your proton ends up going from here, this position, let's say, to this position, and that's essentially what tautomerization is. That takes you from a molecule that's something that's redox active to something that's either difficult to oxidize or completely redox inactive. And so if you can essentially tune the pKa at this site so that the proton really wants to stay, essentially, and doesn't want to move, then that's actually a big advantage towards suppressing tautomerization. So pKa engineering is one of them. We also found a weak correlation with redox potential, which you sort of expect to be the case, right? As that NH bond is stronger, you're going to have a higher redox potential. So there's a weak correlation between so as a high redox potential and resistance to tautomerization as well. So so those two design rules are at least are those I can share that seem to be pointing in the direction of lowering or increasing susceptibility to tautomerization.
Thank you. Yeah, I look forward to reading your paper soon, I hope. Good luck.
Yeah. One thing I will mention real quickly is that I didn't mention anything about neutron spectroscopy or neutrons in this, but in principle, neutrons can provide more chemically specific information about the decay products and intermediates than something like UV-Vis, which is more of a fingerprinting tool. So that's just something I'll throw out there given the nature of the symposium, but I wasn't, unfortunately, I wasn't able to delve into that possibility.
Is it easy to get the deuterated versions of those?
You can, yes. And in principle, you can try to, you can get deuterated versions of these molecules. You can do these experiments in D2O as opposed to water. And that could, in principle, get you detailed chemical information under operando conditions.
Thank you so much. And I think it's time to thank all of our speakers and also the panelists and attendees. And I also want to share my screen for just one last time. So for those in audience who are considering to be users, right? So the first step is always a submit proposal, right? So we so there are good resources. So that link how to submit proposal. So we have now have a good resources for the first time users, especially on what it takes to put together a competitive proposal. And of course, all the members of SHAG EC would be happy to answer any questions. Okay, and with this, thank you so much, and I'll see you around.